Well, hello. Today we're going to have a look at some differential equations, and they're a special kind of differential equation, these ones. These are differential equations of the type dy dx equals a function of y. That is not a function of x, but a function of y. So, how do we deal with those? Well, it's easy. So far we've had a look at what I call type 1 differential equations, and they are just straight differential equations, first order differential equations as we call them, because it's just the first derivative we've got in the equation, and they are equal to a function of x of some kind. Then we have the type 2, as I call them, where you've got a second derivative equals to a function of x, and those are called second order differential equations because you've got a second derivative in them. Now, today we're going to have a look at these ones, these new ones. These are the fun ones because they flip. They flip type 3, and they are dy dx equals a function of y, okay? Y o y, we'll find out. Now, let's have a look at these four, and let's just start off with a bit of a preamble here. Okay, if dy dx equals a function of y, not of x, you use the flip technique. What am I talking about? Well, let's show you. This is number A we're going to have a shot at now. So we've got dy dx equals 2y plus 1, where y has to be greater than minus a half, and you'll see why in a moment. Now, we've got a problem here, guys, and that is we have to integrate with respect to x. But that's not possible because we've got y on the right hand side. So you can't do that. If I was just to take the integral of both sides with respect to x, the right hand side would be nonsense because you'd have integral of 2y plus 1 dx, and that doesn't work. You can't mix your variables. So we have to find a workaround, and it's the cleverest little workaround you ever saw. You simply flip. That's right, you flip. You turn the derivative to, well, you turn the whole thing upside down. You take the reciprocal of both sides, and you get, therefore, dx dy is 1 over 2y plus 1. Now, that means we can quite happily integrate with respect to y, because we've got y on the denominator of the left-hand side, which is what we're going to integrate with respect to, and the right-hand side is now all in y as well. So don't you think that's clever? Flipping is fun. So let's do it. Yeah, that's right. So we integrate now with respect to y, and later on, that'll give us x as a function of y, but then we're going to make y the subject with a little bit of fooling around at the end. But it's just as satisfactory an end result, I can assure you. Okay, so let's go for it. We're saying that x is the integral of 1 over 2y plus 1 with respect to y. Okay, well, I can smell a log coming on, can you? I think so, etc., etc. Yes, let u equal 2y plus 1. But when you get good at these and you don't need to use the training wheels method, you can just see what to do. It's going to be half of log with the base at e of the absolute value of 2y plus 1. Now, I'm just thinking that you don't really need those modular signs there, because 2y plus 1 has to be greater than 0, doesn't it, if y is greater than negative a half. And by the way, have you figured out yet why y had to be greater than negative a half? Well, look at the line after the line that says flip, exclamation mark. Just imagine what would happen if y was negative a half. You'd have 0 on the bottom line, which wouldn't work at all, okay? That would be a disaster. And of course, we have to have y greater than minus a half, so that the term behind the log in the bottom line is going to be positive. Da-da-da-da, the old positive log trick. Now, what we're going to do from now on is we're just going to solve this thing for y. Snail trail. And away we go. Okay, now it's just algebra from now on, so just fasten your algebra seatbelts. Here we go. Yes, I think that's right, isn't it? X minus c multiplied by 2, yes, that gets that. line. I don't need the modular signs, but I've just left them on there for the moment. And therefore, 2y plus 1 is e to the 2 open bracket x minus c. Now that's what you get when you rearrange that expression, okay? You've got to know how to do that, and that's essential to solve these differential equations, okay? So, yeah, so e is the base, and 2y plus 1 is the number, and 2 bracket x minus c is the index or the log, okay? That's how you translate them. Now, let's just take the next step. Yes, what I've done there is I've said 2y plus 1 is e to the 2x times e to the minus 2c. Now, why did I separate those terms out? Well, the reason is that e to the minus 2c, look, I really don't care what c is, really, because it's just a constant, isn't it? And e to the minus 2c is really just a different constant. So, really, there's no particular reason to want to work out c by itself. It's just agglomerated into that term, which in itself is a constant. So I'm going to rename that as, yes, okay, oh, well, I haven't quite renamed it yet, but I've just fiddled with it to basically make y the subject. Now I'm going to rename it. So let a half of e to the minus 2c equal a, capital A, a constant. That seems to be the favourite term to use in these things. And then we get the final answer, and there it is. How sweet it is, okay? A, e to the 2x minus a half, okay? And that's ready to box. That's ready to box. Mr. Box, are you there? Ah, he's there. And there it is, you see. So isn't that something else? The flip is fun. You basically do this ingenious little trick of flipping everything and then integrating with respect to y rather than x, and then you fiddle at the end to make y the subject. Do you love it? Oh, I'm sure you do. Okay, let's have a look at another one now. Oh no, that's the calculator version. Yes, if you were in a calculator exam, you can use this nifty little command called dsolve, which means differential equation solve, and you get it from the calculus menu, right down towards the bottom. You'll see it, DE solve. And it goes DE solve y dash means the first derivative of y. Then you put in the function, which is 2 times y plus 1, and then a comma, commas between each of them. And then you put in your independent variable, which is x, and then you put your dependent variable, which is y. And when you do that, you will get the answer. The calculator fiddles with these annoying little things called parameters. C3 in that screen there on the right hand side is just really means a constant. It comes up with these C1 and then C2 and then C3 and then C4, depending on what it's used before in previous calculations. So that's all that is. So that's really equivalent to a e to the 2x minus a half, which is what I got, okay? So that's a handy calculation to know, or calculator command to know how to do. All right, I think we're ready to go now. Good, let's go on to number B, okay? B for you and me. And it's, have a look at it. Is it a type 1? No, because it's not a function of x on the right. Is it a type 2? No, because it's not a second order DE. Is it a type 3 with a function of y on the right? You better believe it is. So we're going to do the fun flip again, okay? Yes, see? The denominator of the derivative is x, but the function itself is in terms of y, so we've got to do the flipperoonie. Let's go for it. Therefore, yeah, dx dy equals 1 over e to the 2y, or e to the minus 2y, okay? Now, it's easy now. We're just going to integrate with respect to y. And we get that. I hope you got that as well, did you? Well, that's the way to go. Now, we've just got to fiddle now with algebra to make y the subject. So there's the first step. I took c over to the other side with the x, and then I times both sides by a -2, okay? And I get that. Now I'm going to have to take the log of both sides to get that y away from the exponent on the right hand side into the land of the living, not in the exponent world, into the normal world. Okay, you know what I mean? Yeah, that's right. So it's minus 2y log of e to the base e, which is just 1, is equal to the that expression there. So basically what I've just done is I've just put the right hand side on the left hand side and the left hand side on the right hand side after having taken the log of both sides to make y the kind of the subject. Now I'm nearly there now. I'm just about there. So I've just got to get y as the subject, and that line does it. But that's causing me a great deal of concern, that thing behind the log. Remember, log has to be taken to hospital if you give it a negative, something negative to chew on, and we can't do that. So therefore, it's telling us that c must be greater than x. You really need to put that in as a little caution or a caveat on the solution. Otherwise, poor old log, we could give him a very, very nasty accident. Okay. Box. Hello, Mr. Box. That's terrific, isn't it? So how did you go with that? Do you see? Flip is fun. Well, let's do C. C for you and me. What's that one? Oh, goodness. That's a square rooty one. Well, look, you can still see it's a type 3, isn't it? Definitely, because the function on the right is a function of y, and the denominator in the derivative is x, okay? So that means we better fix that one up and go for it. Yes. Now, yes, we know all that, Mr. Computer. We figured it out. So we flip a Rooney, okay? Therefore, dx dy is that, isn't it? So now we've got to figure out how to integrate that thing with respect to y. And I can smell an inverse sine, I think. Can you? Do you remember how to integrate that? It's inverse sine or arc sine. Y plus c. Now, we've got to fiddle now and make y the subject, okay? So what do we do? That's pretty easy. That just means that y is sine of x minus c, okay? So that's pretty exciting, isn't it? It was pretty easy, and just let's finish it off now and put the box around it. Mr. Box, you've come to see us again. We're delighted to see you because we've got our answer. And that's it. Now, I think I've got the calculator versions on the next screen for B and C for you and me. This one's B. And that one's a little bit more complicated now. See, I did the dsolve command on the top line. Dsolve open bracket y dashed equals e to the 2 times y, comma, independent variable x, that is, comma, y, that's the dependent variable, close bracket, enter, and I got the right-hand side. So that's all right, but you can see that it's written with x as the subject, really. And I don't want x as the subject, I want y as the subject. It's got that funny parameter thingy in there too, that C4 thing. So that just means plus c. But then what I did was in the next line, I thought, well, I don't want that, I'm going to solve it. So you use the solve command from the algebra menu, and I copied down that expression on the top right, and then put solve all that, comma, y, which means 4y. And I got that fairly ridiculous looking expression on the right hand side, which, look, if you really want to analyse all that, it is equivalent to what I got. But, you know, sometimes the calculator gets a little bit, well, shall we say, weird in the way it expresses its solutions. But it is correct, okay? And the parameter thing really doesn't help us. It gets into a bit of the land of gobbledygook. But, hey, it did work, and I'm just showing you how to do it, okay? So you'll know how to use that CAS calculator. Yes, that's good. That's B. Now C for you and me. Here it comes. This is C. Same situation here. I did the dsolve command for the DE itself. I got x in terms of y on the top right, so I did the solve command on the second line from the algebra menu, and I got that expression on the right, which is y equals sine of x plus something, C5 now. See how it updates one number at a time every time you do something to indicate it's not really the same constant as in the previous calculation. That's all that does. And it's putting some expression for what x has to also be. And I never take much notice of that anyway. I know what that's doing. That's just it's just giving you a domain for x. Oh no, I really can't figure that out, and I can't be bothered. Who cares? It doesn't matter, okay? So that's, yes, we did that, yes, we did that, and yes, we did that, and we got our answer. So we're smiling all the way here. Let's go and do number D. Okay, let's have a quick look at it. Definitely a type 3, because it's a function of y on the right, isn't it? And apparently y has to be between -1 and +1. Oh, I know what that's for, because it'll be the to do with the denominator, I think. Oh, that's just when we flip it, I think. But let's just keep going and do the flip. Here's D for you and me. dy dx equals that thing. Now let's do the flip. Baruni, yep. There it goes. And then you got dx dy equals that. Now, why does y... Oh, yeah. Of course it does, guys, because if you square y... Oh, yeah. See, if y was outside that domain, you would have... What would you have? Well, let's just keep going. Yeah. And, no, that's all right. That's fine. I'm just going a bit crazy here. So x is equal to that thing. Now that's... Do you recognise how to do that? I hope so. That's partial fraction. Okay, we've got to reduce that to a partial fraction. Okay? Right, so let's go. Partial fractions. Yes, it is. And we've got to just separately do the partial fraction thingy before we can proceed with the integration, right? So let's do that. So that bottom line is how you do the partial fractions, and we've got to solve it for capital A and capital B. All right? Now, snail trail away, and hence we get that thing. And now, this is the clever way of solving these things. We don't have to multiply it all out and get rid of the brackets and equate coefficients. When you do it with this technique, when the degree of the y term is the same in both of those brackets, you can just cleverly, strategically pick a value of y and knock one of those terms out. Okay, so that would give us, in that case, 1 would be 2b, if you think about that, because the a term is going to disappear. Okay, and therefore b is a half. Now on the next line I'm going to cleverly pick y is +1, and if you put +1 into that expression on the top line there on the right hand side, you're going to get that, and therefore a is a half. Yeah, that's what it is. Okay, now let's just see what we get now. We've got our partial fractions. That's what we're dealing with now to take the integral of. Now, what I always do, by the way, is I always recombine my partial fractions just on a piece of paper or in the side margin or something, just to check that I actually did it correctly. It should recombine into the original expression, which I have done just prior to doing this recording, and it did work, so I'm pretty happy with that. Okay, so therefore x is that when you take the integral, and okay, see, y's got to be within that region in the question, because those things will always come out to be positive then. Okay, I think that's positive, yes, that's right. 1 minus y has to be always positive. Yes, it does. And 1 plus y, yeah, always has to be positive. That's why y has to be in that domain. We've got it worked out. Hooray. So therefore x is, we don't need the modular signs anymore, because we worked out those expressions have to be positive. Now, it's all just about algebra now to make y the subject. Now, there's a bit of work to do, so let's go for it. Okay, now I've taken c over to the other side, and I've multiplied both sides by 2, and now I've got that expression, okay? Now, that's where we are. Let's go from there, shall we? Okay. Now, what's the next line? What would you do for your next line? I would do, therefore, e to the 1 plus y over 1 minus y is equal to... No, that's not right. No, that's wrong. It's e to the 2, open bracket, x minus c, close bracket, is equal to 1 plus y over 1 minus y. That's what it is. Yeah, now did you get the same thing? See, I nearly came a cropper there, but hey, I recovered it at the last minute. Now, we've just got to make y the subject, but look, that e to the minus 2c thing sitting in there, that exponent bit, which is a constant, is a bit of a worry. So I think we might sort of do a bit of work on that. Yeah, that's right. That's what we need to do. I'm going to rename that e to the minus 2c thing a constant. I'm going to call it capital A. Okay? Yeah, that's what we traditionally do. Now it looks much cleaner, doesn't it? Because I don't care what c is. It's all agglomerated into a great big constant term anyway. So let's just go with that. Right, now it's just algebra now. We've just got to make y the subject. So we're going to solve for y. And... good, you agree? I multiplied both sides by 1 minus y. Now, what happens now? I'm just multiplying out the bracket now. Now I've got to collect mother duck, get her ducklings together, collect the y terms together, and take everything else over the other side. So that rearranges some of the left-hand side and some of the right-hand side to make that new expression. And I think we're very, very close to the end now. We've nearly got y, haven't we? So let's work that out. So y is a e to the 2x minus 1 over a e to the 2x plus 1. My goodness, how exciting is that? And that is our answer. Whoopie-doo. Okay, we did it. We did it. Now, I think the calculator version is coming up now. Now, this is an example where the calculator just gets a little bit too precious for its own good, and it just goes quite mad. So what we've done here is we did that as we should have done, and we got this expression, which is correct. But it's in terms of x, isn't it? So if you want to make it in terms of y, I did the old solve technique, but look what I got. My goodness. So that's where old Mr. Calculator gets to be a bit of a hindrance rather than a help. It's probably right. It's probably the same as what I got. In fact, I'm sure it would be. But look, can you be bothered trying to work all that out? It's just algebra soup. So at that point, when you're in an exam and you're in a hurry, you just abandon ship and you just go with what you had, okay? Calculator syntax is becoming very unhelpful, to put it mildly. So go away, Mr. Calculator. We don't want you if you're going to do that to us. I think that's the end. So, yes, well done. It's just well done to you, well done to me, and it was easy as 1, 2, 3, wasn't it? So, the flip technique for type 3 differential equations. Have some fun with those, and we'll see you next time.